This is Advanced Higher Electromagnetism, Electromagnetic Radiation. First of all, we have a look at a little bit of a background about James Clerk Maxwell. James Clerk Maxwell, born in Edinburgh, is one of the most influential scientists of his time. Albert Einstein acknowledged that the origins of the special theory of relativity lay in Clerk Maxwell's theories, saying that the work of James Clerk Maxwell changed the world forever. Indeed, it was the work of Maxwell which led to further research into electromagnetic radiation, the development of television, mobile phones, and radio. And through the work with Maxwell and Tesla, he's the reason why we have Wi-Fi technology today. The other great physicist, Richard Feynman, said, 10,000 years from now, there will be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the law of electrodynamics. And this is where we look at the relationships between electricity and magnetism, indeed electromagnetic waves. And there is a statue of him and his dog in George Street in Edinburgh. Electromagnetic radiation. Maxwell managed to unify the theory of electricity and magnetism into a single theory of electromagnetism because he saw that they were entwined with each other. He showed that electromagnetic radiation exhibits wave-like properties, and these waves travel at a fixed speed, which we know to be the speed of light, 3 × 10⁸ meters per second. Electromagnetic waves have both an electrical and a magnetic component, and these oscillate in phase but at right angles to each other, and also always oscillate towards the direction of the energy propagation. This is shown in this diagram. So we can see the magnetic field waves in phase with the electric field waves. The oscillations for both the electric and the magnetic fields are at right angles, that's perpendicular to the direction of the wave. So in this diagram, the wave is traveling from left to right. The propagation of the waves goes along towards that direction. However, the particle movement is up and down for the electric field and left to right for the magnetic field. This indicates that the wavelength of the electromagnetic waves is the same for both the electric wave and the magnetic field, as they oscillate in phase with each other and have a constant phase relationship. The speed of light. Maxwell developed a series of equations that predicted the electromagnetic waves should propagate at a constant speed. This prediction arose from the combinations of 2 other fundamental constants that came from earlier work on electric and magnetic fields, and you've come about some of these already. First of all, we have the permittivity of free space, epsilon naught, 8.85 × 10⁻12 farads per meter. And also the permeability of free space. Mu naught is equal to 4 × 10⁻7 henries per meter. And you've come across both of these before. However, what Maxwell did was combine them together in order to determine a value for the speed of all electromagnetic waves. And this is the equation as appears on your relationship sheet. If we take the known values for the constants of permittivity of free space and permeability of free space, both of which are on the data sheet of your exam papers, we get a value for the speed of light to be 3 × 10⁸ meters per second. So epsilon naught and mu naught are both constants within physics, and because we're determining the value of c, the speed of light, from 2 constants, it itself is a constant value. We can have a look at the unit analysis for this. Here's our equation, and here are the units for epsilon naught and mu naught. We take those units, we can then do substitutions for the different values in order to determine c as being measured in meters per second. Although you're not always expected to be able to quote this proof is not required within the Advanced Higher course. You could have it as part of a problem-solving question. Therefore, we can see that c, the speed of light, speed of all electromagnetic waves, have units ms⁻⁻1, but the speed is not measured relative to anything and therefore must be constant for all freely moving observers. So it doesn't matter where you are observing the wave, it doesn't matter at what velocity you are moving, the speed of light is constant. And we looked at this before in higher when we were looking at special relativity. Special relativity and the postulates around the special relativity came from Maxwell's work. It led Einstein to his postulates about special theory of relativity, but that's a whole other story that we looked at in higher. So let's look at some exercises dealing with Maxwell and some of the uncertainties involved. It is very unlikely that you're going to be asked to determine the value of the speed of light using the constants for epsilon naught and mu naught, the permeability and permittivity of free space, which comes from the data table. However, in looking at your uncertainties, you may be given experimentally measured values of both of these constants and asked to use those to work out a new value of the speed of light. So in this example, we've got values for the permittivity and the permeability of free space, both of which are given with a certain level of uncertainty. And the first thing you're asked to use is Maxwell's equation in order to determine the value of the speed of light. In fact, in this one, you're asked to show that the final value for the speed of light is 3.4 times 10 to the 8 meters per second. So you could take a minute here to pause the video and have a shot yourself. Here is the solution. C is equal to 1 over the square root of mu naught multiplied by epsilon naught, which is equal to 3.39 times 10 to the 8 meters per second, which rounded gives you 3.4 times 10 to the 8 meters per second, as required. For the next part, we're asked to show the result of the permeability of free space has the largest percentage uncertainty. So you should be aware how to work out the percentage uncertainty. For epsilon naught, the permittivity of free space, the percentage uncertainty is equal to the uncertainty value, which in this case is 9 times 10 to the negative 13, divided by the value given, 8.8 times 10 to the negative 12, multiplied by 100, which gives us 10.2%. Now, normally we would give percentages as whole numbers. We wouldn't have a decimal place. However, I'm keeping the decimal place here just now because we don't know what the other values are. We may need to compare them later on. For the permeability of free space, the percentage uncertainty is equal to 1.5 times 10 to the negative 7 divided by 9.9 times 10 to the negative 7, again multiplied by 100, and that gives you 15.2%. So indeed, the permeability of free space has the largest percentage error. As is often the case with percentage uncertainties, we need to combine this, and we're asked to calculate the percentage uncertainty and the value for the speed of light. So just a reminder about the equation, C is equal to 1 over the square root of epsilon naught multiplied by mu naught. So first of all, let's work out the percentage uncertainty combination. We know for the permittivity of free space, we have a percentage uncertainty of 10%. And for the permeability of free space, we have a percentage uncertainty for 15%. So the percentage uncertainty combined is equal to the square root of 10 squared plus 15 squared, which is equal to 18. However, we need to take into account that we're square rooting the epsilon naught multiplied by the mu naught here. So if P is equal a to the n, therefore the percentage uncertainty in P is equal to n multiplied by the percentage uncertainty in A. So here, C is to 1/2. So C is epsilon naught mu naught to the negative 1/2, which means that the percentage uncertainty in C is going to be 18% multiplied by 1/2, which is equal to 9%. So we've got to be careful here with our uncertainties. It's not just the combinations of the uncertainties. We need to take into account that we're square rooting the values of the product of epsilon naught and mu naught. We're then asked to calculate the absolute uncertainty in the value for the speed of light. Well, the absolute uncertainty comes from the percentage uncertainty. We've said that the percentage uncertainty is equal to 9%. So the absolute value is going to be equal to 9% of our calculated value, which was 3.4 times 10 to the 8 meters per second. Which works out to be 3.06 times 10 to the 7 meters per second. So we're writing the absolute uncertainty and the final uncertainty. What we would say is we'd say our value for C is 3.4 times 10 to the 8 plus or minus 3 times 10 to the 7 meters per second. And we find that if we take 3 times 10 to the 7 into account with our uncertainty, we'd end up with a range of values which include 3.7 times 10 to the 8 to 3.1 times 10 to the 8 meters per second, which is actually pretty close to the actual value. We're asked to comment on the accuracy of the experimental results here. Well, as we said, we have a value for the percentage uncertainty. We have a value for our absolute uncertainty. Just to remind you of that, that was 3.4 times 10 to the 8 plus or minus 3 times 10 to the 7 meters per second. Within the range of uncertainty, the best value we have is 3.1 times 10 to the 8 meters per second. How accurate is our value? Remember, accuracy is about how close we are to the actual value as opposed to precision, which is how precise, how many decimal places we can measure a value to. So how close is 3.1 times 10 to the 8 meters per second to 3 times 10 to the 8 meters per second? We could work that out and give ourselves an absolute answer to that. So we're within 0.1 times 10 to the 8 meters per second. 1 times 10 to the 7 over 3 times 10 to the 8. .03 times 100, 3%. So we're actually within 3% of the actual value for the speed of light. So in terms of the experiment, we can say that this is pretty accurate.